Okay, well, let me see if I can make this work. This is my first time to do it on Linux. Alright, so the basic equation that we're going to be dealing with is here. This one here. We'll just do it in 2 dimensions, so you see x derivatives and y derivatives. You have du dt. U is the function that we're interested in, that might represent pollution levels or disease levels or something like that. So we have du dt on the left-hand side. On the right-hand side, we divide the operator into 3 parts. The first part has a mixed partial derivative. That's a little difficult to deal with. The second part, f1, has only x derivatives. The third part has only y derivatives. So in the spirit of ADI, we're going to be dealing with these parts separately. Now, as far as discretization is concerned, uxy, the meaning of uxy, is given down here. And this is all taken from the paper. I've given you the references. f1 that depends on the x derivatives will be c1 times this discretization plus d11 times this discretization. f2 will be the y derivatives here and here. Okay. Now practically, how does this work? You're going to have a series of equations. This series of equations will be contained in a loop, because at each time you go through this entire loop, you update t by delta t. For instance, you start at t equals 0, then after one iteration of the loop, you'll have u at time delta t. After the second iteration of the loop, you'll have u at time 2 delta t, and so on. We start with u0 and we'll continue to update. You can see that un is u at the current time, un minus 1 is u at the previous time. So we'll start with u0, we'll have initial conditions for u0, and we'll go through these series of equations to arrive at u1. Once we have u1, we'll plug back in to find u2. Now all of these y's are simply accessory quantities. They're intermediate quantities that we don't need to save. They're only used in the computation. If you notice, the second line here has yj for j equals 1, 2 up to k. In our case, k equals 2. We have f1 and f2. So this second equation here actually represents 2 equations. One will take care of f1 and one will take care of f2. Okay. Notice here also that yj depends on yj minus 1. So when you compute y1, it's going to depend on y0. That's why you need to compute y0 first. Then when you compute y2, it will depend on y1. Note also in this second equation that yj appears on the left-hand side and on the right-hand side. What you're going to need to do is take these terms on the right-hand side over to the left and use a tridiagonal solver to solve for yj. Okay? All these other quantities you have available. When you're computing y1, for instance, you know y0. Theta is a parameter. Delta t is a parameter, fixed parameter. Fj, in this case when j equals 1, fj will refers to f1. And here you'll evaluate f1 for, as I said, the current time and the same yj that you're looking for. And then you'll also have fj at the same time at the previous time for the previous solution u. All right, the third line it's similar. This one you can solve directly. Notice that y0 tilde only appears on the left-hand side, and y0 tilde is expressed in terms of quantities that you know. Yj tilde is similar to yj. In fact, I'm sure you can reuse the same code. If you see the similarities here, the only difference between yj tilde and yj is that the untilde quantities are replaced with tilde quantities. Okay, so you'll have the same computation, but you'll have with different substitution. Also notice that here you have un minus 1, and here you have yk. Yk being the very last y that you computed here. Since in our case k equals 2, because we have f0, f1, f2, in this case, in our case, we will have k equals 2. So let me just write that out. For us, we're going to have k equals 2. Okay, so this is going to be equal to k equals 2. All right, now that's still a little bit sketchy. Let me I wrote out some of the equations that you're going to be using. And let's see where we are. Okay, all right, a little bit fuzzy, but hopefully you can still see this. All right, so when you start out, you're going to start out with u. Let me see if I'm here. Not sure why it's not registering. Well, I'm not going to be able to write on this, so I'll just talk through it. Let's see if I can do with this. No, it's not going to write. Okay, so here we start with, I don't know what it's doing. Okay, maybe it'll work now. Okay, I'm not used to this program. All right, so you're starting with uij. That will be your initial function. As I said, you can think of u as a pollution level, something like that. So when you start out, each uij can be a random number between 0 and 1. That's just a good thing to start with. Now the other thing is that u on the boundary, I don't know why it's jumping around. Let's try this. Okay, u on the boundary is specified to be 0. So I'm saying, for instance, that I and j run between 1 and 8. So that means that u at the left-hand side and u at the right-hand side is going to be 0. So u of 1j, u of 8j is equal to 0 for all j. U of I1, u of I8 is equal to 0 for all I. So if you think of this area as a square, you have a square grid, and the values of u on the edges of the grid will all be 0. All right, so remember, we had 5 equations. The first one was for y0. So if you want the explicit equation for y0, it's here. y0 will be u of ij. So you'll have to do a loop through I and j to implement this. y0 at the site ij is equal to, by the way, ij are the sites on the grid. Just to make clear about that, you're going to have grid points here. I'm not sure how the indices work in C++. I'm having my indices start at 1. You can translate appropriately. All right, but your I and j are positions on the grid. So for each I and j in the grid, you're going to have to do this update. y0 of ij equals u of ij plus dt. dt is a parameter. You'll have to define that. Divided by 4 times dx times dy. These are also parameters. These indicate the size of the grid spacing. You multiply this by d of 1, 2 plus d of 2, 1. All right, those are parameters that you'll have a matrix D which is given. And if you go back here, you can see that that reflects this part of the equation here. Okay, so right now I'm doing this first equation here. Okay. And I started with a u. Now I'm doing delta t times this part. Okay. So let me go back. All right. Now this is the f0 part. I've just put in the discretization for f0. It's a little bit complicated, but you can refer back to the documentation to make sure you have it right. Okay. So this is a plus here. Okay. All right. Okay.
Do you have to
Okay. Okay. All right. So so this here is just the discretization of the f0 that was given in the other document. Okay. And you can compare this with the other document. This b represents beta, but all I've done is taken the discretization here for uxy, and I've rewritten it. Okay, so that this uxy d12 plus d21 times uxy is what's going to go in for f0, and f0 is the first part of f. Right? Similarly, you're going to have to do stuff for f1 and f2. Now notice that f1 is a combination of c1ux plus d11uxx. So you're going to have c1 times this part plus d11 times this part. And you can see I've written that out here. Right. So this is c1 times the first part plus d11 times the second part. This is, of course, you have the dt also. Right. Then finally have the same thing for f2. Right. So that's a repeat. You can see if you can follow that. Right. Now let me move down. So this whole thing here, everything you see on this page, that's the discretization of this. Let me get there. That's the discretization of this first equation here. Now the second equation is a little more tricky because, as I mentioned, yj appears on the left and on the right. So let's see how that works. All right, so let me see if I can scroll down here. Okay, so as I mentioned here, y1, you need to take all terms with y1 to the left-hand side. All right, the term that involves y1 is f1 of y1 times theta times dt. So I brought that to the left-hand side. And that's, we have here y0 minus theta times dt times f1 of u. Now u is what we know already, so that's okay. We can evaluate f1 of u. You're probably going to want subroutines to evaluate f0, f1, and f2. That should make things a lot easier without having to rewrite all of this stuff. But in this case, you're going to have to write out f1 explicitly, because here you have y1 of ij. If you write out what f1 is, it involves y1 of I plus 1j, y1 of I minus 1j, and here we also have y1 of I plus 1j, y1 of ij, y1 of I minus 1j. Now you're going to have to group together the terms that have y1 I plus 1 of j. There are two terms here that both have that quantity. And you're going to have to group together the terms that have y1 of ij. There's one here, and then there's one here. And you'll have to group together also the terms that involve y1 of I minus 1j. That's one here and one here. So you're going to get something like, that has some constant. Let's see if this works. You're going to have some constant times y I plus 1 j plus some other constant times y I j plus some other constant times y I minus 1j. And you're going to have that on the left-hand side, and that's equal to this stuff on the right-hand side, which you can evaluate directly. All right, now notice that the j is the same for all of these. So for each fixed j, that is, you're going to have to loop through j, and for each fixed j, you actually have a tridiagonal equation to solve. Now you should be able to solve this with the tridiagonal solver, and once you've solved it, you'll have equations for y1 of all i's with y-coordinate j. Okay? All right, so that's the only one I did out explicitly. When you do the y0 tilde here, that's going to be very similar to the y0 here. When you do the yj tilde here, that's very similar to the yj. Now remember, I only did y1 here explicitly. y2 is going to be very similar. y2, you'll set this up, you'll pull out the f2 term here, pull that to the left-hand side, and then you'll have a tridiagonal equation with constant I, and you'll solve that for all j's. All right. Now the reason for all this contortion, which seems a lot more difficult than other versions, is you get much more rapid convergence. The whole point of this project is to do very fast code, to optimize the code for speed as much as possible. So I think that pretty much takes me to what I wanted to say, so I'm going to stop.